Thank you, Marcus, for the introduction, and thanks to all of the organizers for giving me the opportunity to present. What I'll be presenting today is based on work that I am currently doing with my co-supervisor, Alexander Smeding. And so my goal has been to develop some sort of analog of quantum harmonic analysis on the Riemannian manifold, by which I mean that RD is replaced by a Riemannian manifold. This was a project suggested by Franz at the conference in Trondheim a couple of years back. And so my goal today is just to give you a sort of brief philosophical kind of overview of this project. And so I hope you'll forgive me for glossing over a lot of details and not defining everything properly. Okay, so let me begin by describing the setting. So M is going to be a d-dimensional Riemannian manifold, which is a smooth manifold with a well-defined notion of length and angle. Then Tm is going to be the tangent bundle of M, which is a smooth manifold of twice the dimension that M has, so 2 times d in this case. And T star M is going to be the cotangent bundle, which, so we construct the tangent bundle by taking all the tangent spaces to our manifold M, so one for each point, and then gluing these together into a smooth manifold. And T star M, the cotangent bundle, is constructed in much the same way, except that instead of taking the tangent spaces, we take the dual spaces to the tangent spaces. And so on this illustration, where M is the circle, we can identify both the tangent bundle and the cotangent bundle with the cylinder. And so these red vertical subspaces of the tangent bundle, these are then identifiable with the tangent spaces of our manifolds, and we refer to these as the fibers of the tangent bundle. And similarly for the cotangent bundle, so these blue vertical subspaces are the dual spaces of the red ones, and we refer to these as the fibers of the cotangent bundle. And so a point on the tangent bundle corresponds to a vector v tangent to our manifold at some point x. And I'll denote this by the somewhat redundant tuple xv. So x denotes the tangent space from which we draw v. And then similarly for the cotangent bundle, so a point on the cotangent bundle is given by a linear functional omega on the tangent space to our manifold at some point x. And I'll denote that by the tuple x omega. And if I need a second point on the cotangent bundle, I'll use y eta. And then in the end, we will see a handful of quantum harmonic analysis-like results, but these will necessarily only be asymptotic. And so we can't just consider the classical system and the quantum system separately, but we have to think of the classical system like a limit of the quantum system. And so to do this, we have to introduce this semi-classical parameter h. And so quantization in this context should be an h-dependent family of maps for non-zero h. I denote these maps by q sub h. They take functions on the cotangent bundle and produce operators on L2 of M. And I'll denote the generic function on the cotangent bundle by little a. And so each such function using these quantization maps gives rise to a family of operators on L2 of M, indexed by the non-zero values of h. Then let's briefly recall how Weil quantization works in the Euclidean case, so where M is equal to Rd, and a is a function on r to the 2d. So there we can define the Weil quantization of a, this operator, in terms of its integral kernel. And we obtain the integral kernel of this operator from the function a using a couple of ingredients. The first of these is this partial Fourier transform f sub 2, which is a Fourier transform with respect to the last d variables of our function a. And then we also need this coordinate transformation, which takes a pair of points, x, y, on our manifold, and gives us x plus y over 2 and x minus y over h. And so what I'll present now is a geometric generalization of these ingredients, which gives us a geometric generalization of Weil quantization. And this is due to Landsmann in a paper from '93. So first of all, we generalize this partial Fourier transform we had by the fiber-wise Fourier transform. So this takes a function on the cotangent bundle, which is what we want to quantize, and produces a function on the tangent bundle. And it does so simply by taking the Fourier transform along each fiber, which makes sense because these are dual vector spaces. And then for the coordinate transformation. So let's note that in the Euclidean case, x plus y over 2 is simply the midpoint of the straight line from y to x. And on a Riemannian manifold, straight lines are replaced by geodesics, which are the shortest paths between any 2 points. And so we'll simply interpret x plus y over 2 as the midpoint of the geodesic from y to x. And then x minus y has to be a tangent vector to our manifold at this point. And the simplest thing to do is to take the velocity vector of this geodesic at its midpoint. And this is compatible with what we do in the Euclidean case. So this is a geometric interpretation of that. And then using these ingredients, we can define wild quantization just like before. There is a canonical measure on a Riemannian manifold, which we can use to integrate. So we define it in terms of its integral kernel. But there is one issue here, which I'm glossing over, which is the fact that on a general Riemannian manifold, there isn't always going to be a unique or any geodesic between 2 arbitrary points. And so we also have to introduce some cutoff function here, which I'm glossing over, so that won't be relevant to what we're doing today. Okay, so as I said, we're going to obtain some asymptotic results, and so we need to make sense of the statement that the wild quantizations of A can converge to A as H goes to 0. And this is a kind of strange statement, because this is a family of operators converging to some function. And more generally, we want to make sense of the following situation. So suppose we have a family of compact operators on L2 of M, indexed by the non-zero values of H. And suppose we have some continuous function A on the cotangent bundle, which vanishes at infinity. So all function spaces are assumed, all functions are assumed to take values in the complex numbers, unless I say otherwise. And then, given this data, we want to make sense of the statement that this family of operators can converge to this function as H goes to 0. And we will interpret this as A being the asymptotic Weil symbol of this family of operators. And we're going to take the following approach. So we're going to consider all tuples of this form consisting of a function A on the cotangent bundle and a family of compact operators on L2 of M. And considering all such tuples essentially amounts to considering the C-star algebra, this product of C-star algebras. So the first entry is a function on the cotangent bundle, and then we have a family of operators on L2 of M. And then we're going to figure out which of these tuples should be thought of as continuous in H. Because then it makes sense to say that this family of operators converges to A if the corresponding tuple is continuous, because then this is just continuity at H equal to 0. And the way we're going to do this is we're going to construct a C-star subalgebra of this C-star algebra of all tuples. I'm going to call this A for now, and this is going to be the C-star algebra of all continuous tuples. So membership of this C-star algebra is going to define what it means for a tuple to be continuous. And we're going to construct A by first constructing a star algebra of all the tuples we want to think of as smooth. And then we'll define A, the C-star algebra of continuous tuples, to be the closure of this star algebra. And this star algebra of smooth tuples will actually be identified with an actual algebra of smooth functions on some smooth manifold associated to M, noted by this boldface Tm. This is not the tangent bundle of M, it's something known as the tangent groupoid of M. And so my next task is to construct the tangent groupoid. And this is a construction due to Alan Kohn. So I'm first going to define the tangent groupoid as a set, and it's going to be a bundle of manifolds over the unit interval. So this means that I have to specify some smooth manifold for each value of H. And these manifolds will then be referred to as the fibers of the tangent groupoid. And so when H is equal to 0, I'm simply going to take the tangent bundle of our manifold. And then for every non-zero value of H, I'm going to take the Cartesian product of M with itself. This defines the tangent groupoid as a set. Now, I'm not going to properly define the smooth structure. That gets a bit involved. But I'm going to tell you about one property it has, which I think highlights what's going on. So the tangent groupoid has the following property. If we start with a smooth function f on our manifold M, complex valued, then we can construct a function on the tangent groupoid using these formulas. And that function will always be smooth, given that f is smooth. And the function constructed from f is defined as follows. So when h is equal to 0, we have the tangent bundle of M. So we have these tangent vectors v to our manifold. And these are simply going to map to the directional derivative of f in the direction of this vector at the point where the vector is situated. And then for non-zero h, we have these pairs of points x and y in our manifolds. And these are going to map to this difference quotient, f of x minus f of y over h. And so the tangent groupoid has the property that we can smoothly go from difference quotients to directional derivatives. It's a really natural construction in some sense, and it turns up in a lot of places. But I've said that we are going to obtain this star algebra of smooth tuples as the algebra of smooth functions on the tangent groupoid. And so I have to tell you how such a function gives rise to a tuple of the desired form. And so suppose we have some smooth function A on the tangent groupoid. And first of all, I'm going to restrict to the fiber over where h is equal to 0. So this gives me a smooth function on the tangent bundle to the manifold. And I can apply the fiber-wise Fourier transform, or rather its inverse, to this function. And that will give me a continuous function on the cotangent bundle of the manifold. And so that will be the first entry in this tuple. And then if I restrict to a non-zero value of h, for each such non-zero value of h, I get a function on m times m. And that I can think of as the integral kernel of an operator on L2 of m. So that gives me a family of compact operators on L2 of m indexed by the non-zero values of h. And so this is how a function on the tangent groupoid gives rise to a tuple of this form. And so we've shown that we can think of this star algebra of smooth functions on the tangent groupoid as sitting inside this star algebra of all tuples. And then, as promised, we're going to obtain the continuous tuples just by taking the closure of this star algebra. And the resulting C-star algebra is referred to as the groupoid algebra of the tangent groupoid. And so we saw group algebras in RS talk yesterday, and this is a generalization of that to the setting of groupoids. I'm just downplaying the groupoid aspect in this talk. And so here's just an illustration of such a continuous section. And then, as promised, we say that a family of compact operators converges to some continuous function A as h goes to 0 if the corresponding tuple is continuous. So if it lies in this C-star algebra of continuous tuples. And then while quantization actually has a really nice geometric interpretation in this context, which I'll have to save for another time. But if we start with a sufficiently nice function b on the cotangent bundle, and we while quantize it, then we actually obtain a smooth tuple. Okay, so that takes care of while quantization. Another important ingredient in quantum harmonic analysis is the Heisenberg group. And it turns out that there is an analog of that in our setting. It's in no way a generalization or anything like that, but it's an analog, as we'll see. The downside is that this group is infinite dimensional. The group is denoted G sub M, and it's a semi-direct product of groups consisting of the compactly supported diffeomorphisms of M, along with now the real valued smooth compactly supported functions on M. And so a diffeomorphism of M is a smooth bijection with a smooth inverse. And to say that it's compactly supported means that it restricts to the identity outside of some compact set. And since the group is a semi-direct product, I have to tell you how the diffeomorphisms act on these functions. And so given a diffeomorphism phi and a function f, phi acting on f is simply given by precomposing f with phi inverse. And this group has an analog of the Schrödinger representation, so an analog of these time-frequency shifts. So these are unitary representations of this group on L2 of M, one representation for each non-zero value of h, and they're given by the following formula. So we can see that the function f is acting like a very generalized sort of modulation in this picture, a spatially varying modulation. And the diffeomorphism phi is acting like a very generalized translation. So it's acting on the argument of our function. But then, unfortunately, precomposing with a diffeomorphism is not unitary. And so we also have to multiply by this Radon-Nikodym derivative in order to obtain unitary representations. And then this group also has an action on the cotangent bundle, which I denote by alpha 0. And we can think of the group as acting via very generalized translations on the cotangent bundle. And so I won't go into the details of how this is defined. That won't matter to us, but it's defined using very basic differential geometric notions. And then once we have an action on the cotangent bundle, we get an action on functions on the cotangent bundle just by acting on the argument. And then we have to act with the inverse in order to get a group action. And the last ingredient we need an analog of are these symplectic characters. So let's recall that if we have a point x omega in r to the 2d, then we can define this symplectic character. So this is the function on r2d we get by inserting x omega into the first slot of the symplectic form and then exponentiating the result. And if we while quantize these functions, we obtain these symmetrized time frequency shifts, so our Schrödinger representation. And there is also an infinitesimal version of this statement. So given a point on r to the 2d, we define this function h indexed by the point. And this is simply the exponent of this symplectic character. And if we wire quantize these, we obtain the generators of our symmetrized time frequency shifts. So we obtain the derived representation of this Schrödinger representation. And then we have an analog of this in our case. But there is one complication which we're not seeing in the Euclidean case, because there the Heisenberg group is isomorphic to its Lie algebra as a group. But in the general case, we need to index these functions and these generators by the Lie algebra of the group that's acting. And so we need to consider the Lie algebra of our group. So this is a semi-direct product of Lie algebras consisting of the compactly supported smooth vector fields on M, as well as the functions from before. And then for each element of this Lie algebra, we define a function on the cotangent bundle via this formula. Again, the details of this definition don't really matter. The point is that we have analogs of these functions. And if we while quantize these functions, then we obtain the generators of our new general time frequency shifts. So we obtain the derived representation of this Schrödinger representation. And just a quick remark for those of you who are familiar with symplectic geometry. So it turns out that these functions are the generators in the symplectic sense, the Hamiltonians for this group action on the cotangent bundle. And so this formula is really showing that our Schrödinger representation is what you get by quantizing this action on the cotangent bundle. Now we have everything we need to formulate our results. So we define these operator translations in the same way that we always do. I denote these by alpha sub h, one action for each non-zero value of h, and they're defined just by conjugating with these time frequency shifts, so conjugating by the Schrödinger representation. And then we can show the following result. So if we have a family of compact operators with asymptotic Weil symbol A, and we translate all those operators, then the resulting family of operators has asymptotic Weil symbol, the translation of A. And so this is an asymptotic analog of the fact that translating an operator corresponds to translating its Weil symbol. And I should say that Landsmann has a version of this result in his 93 paper, but it's stated in very different terms and proved using very different methods. I'm not 100% sure whether the results are actually equivalent, but this is the result we prove. Then we also prove the following. So this is an analog of the fact that these symplectic characters while quantized to the time frequency shifts. So it's saying that the asymptotic Weil symbol of these time frequency shifts is given by this analog of a symplectic character. And I have to include these weasel words here in essence because this doesn't quite fit into the framework I've been developing because these unitary operators are not compact and these exponentials don't vanish at infinity. But in essence, we can show this, and I'm happy to show you the precise result afterwards if you're interested. And then there is a simple lemma on the tangent groupoid. So given a smooth tuple, if we take the traces of these operators, multiply by some factor of h, and take the limit, then we obtain the integral of the asymptotic Weyl symbol A over the cotangent bundle with respect to this canonical Liouville measure. And using this and our previous result, we obtain the following formula. So this is a bit difficult to put into words, but it's an analog of the fact that the Fourier-Wigner transform of an operator is the same as the symplectic Fourier transform of its Weyl symbol. And this is stated for an arbitrary family of compact operators, so it's really a statement about dequantization from the physics point of view, but we can always take the Weyl quantizations of our function A here. And so I think if we want to continue in this direction, then this suggests how we should think of the Fourier-Wigner transform as well as the symplectic Fourier transform in this setting. Whether that will turn out to be useful or interesting remains to be seen. And that's most of what I wanted to say. I just want to add something very briefly at the end. So there is this whole other side to this story, which I'll have to save for another time. But for those of you who are already familiar with Kirillov's orbit method from representation theory, we can also show that this whole picture I've been painting actually fits into that framework, just applied to this infinite dimensional Heisenberg-like group. So it's usually only applied to finite dimensional groups, although there have been a bit of work on infinite dimensional Lie groups as well. And so I won't bore you with the details. I'll leave this up for now in case you're familiar and want to look at it. But I just want to mention that this is also the same framework that Stine Marie Berge and Simon Haldonsen have been using to formulate quantum harmonic analysis on non-abelian groups. And so I think it's really interesting that these two completely different branches of doing quantum harmonic analysis on non-abelian groups and doing quantum harmonic analysis on Riemannian manifolds actually fit into the same overall framework. So that's all I wanted to say. So thank you for your attention.